Hello everyone. In the last class we have started discussing some channel models. We have discussed some physical channels, their properties, and also some channel models, simplified models with which we can work in, we can develop techniques and find out what is the maximum possible rate at which we can transmit through the channels and so on. So, for doing a good analysis and for finding out techniques for transmitting at the highest rate through the channels, it is important to start with some simpler models first, so that we get sufficient insight into the techniques and the behavior of the channel, and then we can complicate the model more and more and see if we can solve for the more general channels. So, in the last class we have discussed some particular channel models. Binary symmetric channel to start with, that is the simplest model we have discussed, where we transmitted 0 or 1 and we received 0 or 1, and there is a probability of error which is same for transmitted bit 0 as well as 1. And then we have discussed binary erasure channels, for which the transmitted symbol is either 0 or 1 and the received symbol is 0, 1 or erasure. By erasure, what we mean is that a bit which cannot be distinguished as 0 or 1. And then we have discussed binary asymmetric channel, which is basically the generalization of binary symmetric channel, where probability of error for 0 is different from probability of error for 1. And then we have discussed a further generalization of binary symmetric channel, that is discrete memoryless channel, where the transmitted symbol may be taking value from any finite set and the received symbol also may take values from another finite set. And then the channel is characterized by these two finite sets, which are called respectively transmit alphabet and the received alphabet, and also the probability transition matrix, which gives the conditional probability of the received symbol given the transmitted symbol. Then we have discussed discrete channel with memory. It is basically generalization of discrete memoryless channel. We have not discussed this in detail, but this is when the behavior of the channel depends on how it behaved for the previous symbols. And then we discussed discrete channel with feedback, where the transmitter is assumed to know what has been received so far at the receiver, so that the transmitter can possibly use that information for transmitting future values, future symbols. So, one of Shannon's many important results is that with feedback, capacity of discrete memoryless channel does not increase. So, in this class we will discuss some more channel models which are important for practical purpose. To start with, we will discuss continuous valued channels which can carry continuous valued signals. So, we will first consider the discrete time version of such a channel. All the channels we have discussed so far are discrete time. We will continue to assume discrete time channels. So, in each use of the channel, the value that is transmitted through this channel is continuous value. Previously, we have assumed that the transmitted symbol takes values from a finite set. So, it can take only finitely many values. So, 0, 1 or 0, 1, 2, 3, 4 or A to Z having 26 values. So, now we will consider channels which can transmit, through which we can transmit continuous values. So, the simplest model we will discuss is AWGN channel, additive white Gaussian noise channels. Here we have the channel through which we can transmit a real value x, the received value is y, and y is nothing but x plus some noise z. So, z is noise and y is x plus z. Sorry, this is simply z, z is being added, this is noise. So, this is additive because the noise is added to the transmitted signal, then it is white because the noise is assumed to be white noise, that is when we use the channel many times in sequence, the noise samples, that is if we consider the first use as if we denote the first transmitted symbol by x1 and second transmitted symbol by x2 and so on, and similarly denote the first noise sample as z1 and second as z2 and so on, and similarly the received symbols by y1, y2 and so on, then we can denote the ith use of the channel as the following, that is xi is transmitted, zi is added with xi, and we receive yi, which is nothing but xi plus zi. This is the at the ith symbol interval, this is what is happening, and then zi is a noise process, noise random process. And zi is white, which means that the different random variables zi's for different i's are independent of each other. So, this is white. So, this the fact that it has zero autocorrelation, for non-zero lags, that is the correlation between zi and zi plus t for any t is 0. This implies that in the frequency domain the power spectral density of zi, the process zi is flat in frequency domain, that means it is white and it is Gaussian. So, zi is also Gaussian, and let us assume that it has variance sigma square. Sigma square is the variance of zi, each zi. So, these are basically independent and identically distributed with Gaussian with variance sigma square. So, this is discrete time AWGN channel. Now, we can similarly have the continuous time version of this channel, where we will be transmitting a continuous waveform. So, this is continuous time AWGN channel, where we will transmit, instead of discrete samples, we will transmit continuous waveforms. So, xt is a random process, we will transmit, this is the transmitted signal, this is the noise signal, and this is the received signal. This is xt plus zt. This is noise. Just like the discrete time version, this noise is assumed to be white, noise, that is the autocorrelation function of this random process, the noise random process, is the Dirac delta function. It is white and Gaussian. With power spectral density n naught by 2. This is usually the n naught is the one sided power spectral density, n naught by 2 is the two sided power spectral density. So, the power spectral density of this noise looks like this is flat at n naught by 2. Okay. So, this is the continuous time AWGN channel. Now, in both these cases we have assumed white noise, which means that the noise at the present time does not depend on the noise values in the past. So, that itself means that the channel is memoryless, just like the discrete memoryless channel we considered where where each use of the channel is independent of the others. So, similarly, here also the noise values at any instant is independent of all the noise values in the past. That means the noise is independent, noise does not have any memory. So, that the channel itself does not have any memory. What happens to a signal value transmitted now does not depend on what happened to the signal values transmitted before. So, the channels in these channels the channels do not have any memory. Now, the next channel is the obvious generalization of this, that is AWGN channels with memory. So, AWGN channel with memory. So, here we have the same, this is the continuous time version xt, zt, yt, which is xt plus zt, and the discrete time version is same except that t is replaced by a discrete index I. In both these cases previously we have considered zt or zi to be white. Now, the generalization is that zt and zi need not be white. So, their power spectral density need not be flat in the frequency domain, and as a result there is correlation in the time domain in the noise. So, what happens to the transmitted signal at time instance t depends on what happened to the signal values in the past, because the noise values at t depends on or is correlated with the noise values in the past. So, the noise since the noise in different time instances are related, they are correlated, the distortion that is coming, that is affecting the signal at different points of time are correlated. So, the channel has memory. So, simply zt or zi are correlated noise, again Gaussian. Still this is not white. So, this is not white noise. So, this is not called AWGN channel, but additive Gaussian noise channel with memory, because the noise now is possibly not white. If it is not white, then the channel has memory. So, this is not AWGN, but this is additive Gaussian noise channel with memory. Now, channels with memory are also thought of in a different way in practice. That is, previously we have considered channels in general of the form of the following. The signal goes through some function g and then some noise is added. This is the general model of channel we started with. The alphabet may be different, it may be continuous values, some continuous set, it may be some finite set. Similarly, the received value may be from a finite set or a continuous set. The noise itself may be in different form, it may be correlated, uncorrelated and so on. But in the channels we have discussed in this class, we have not considered any G. That means it is directly being just added by a noise. In general, channels can go through some function, and the simplest functions that we consider are the linear filter channels. That is, the signal, let us first take the discrete time version. So, linear filter channel. In this case, G is a linear filter. So, in the discrete time version of the channel, there will be a discrete time filter. This is we have a signal xi and there is a linear filter with impulse response, let us say hi. Hi may be again FIR filter or IIR filter, that is finite impulse response filter or infinite impulse response filter, that is hi may be non-zero for I greater than equal to 0 and it may have non-zero values till infinitely many non-zero values, or it may terminate after some time. After some time the coefficients may, impulse response may become 0. So, whatever it is, there is a discrete time filter and the output of the filter then is added with the noise. So, Zi then Yi. What is Yi then? Yi is the convolution of xi with hi and then plus Zi, the noise, and Zi is assumed to be white Gaussian noise. And the continuous time version of this channel is simply xt ht is the impulse response, this is zt, and the received signal is yt is xt convolution ht plus zt. So, if you are more comfortable with the discrete time signals being denoted by xn instead of xn like this, so these will then be denoted as xi instead of xi. So, here we have denoted such a signal as xi instead of putting the I in brackets. So, these should be thought of as discrete time signals going through a discrete time filter, and a discrete time noise is being added to the output and we receive a discrete time signal. Similarly, here we have, instead of everything discrete, we have everything continuous time. So, the continuous time channels are also called waveform channels because they because we transmit waveforms through such channels. So, continuous time AWGN channel, continuous time linear filter channel, continuous time additive Gaussian noise with memory, they are called waveform channels. Instead of calling them continuous time channels, we can also call them waveform channels because we transmit continuous time signals, that is waveforms, through the channels. Okay. Now, we have discussed this linear filter channel, and here also we see that what happens to the signal now depends on what happened before, that is what was transmitted before. In other words, what we receive now depends on not only what we transmit now, but also on what we transmitted before. And as a result, these channels also have some kind of memory, that is they remember what happened in the past. So, there is also some relation between this linear filter channel and the additive Gaussian noise channel with memory that we have discussed just before this, because both of them obviously have some kind of memory, and this form of channel can be converted with some operation at the receiver to a channel of the previous type, and a channel of the previous type can also be converted into a channel of this type with some manipulation at the receiver. We will see that now. Suppose we have a linear filter channel where we have Xi, there is a linear filter channel, linear filter with Hi impulse response, and then a noise is added Zi, we have Yi, which is Xi convolution Hi plus Zi. Now, suppose that we can implement some inverse filter of this. We will not go into the intricacies in the design of the inverse filter. It may not be stable and all such intricate issues we will not go through, but let us say we have an inverse filter of this channel filter. Suppose that Gi is the impulse response of the inverse filter. This is the impulse response of the inverse filter of Hi. Then what we can do is, at the receiver we can simply pass the signal through that filter Gi. This is Yi we actually received, and then we passed it through Gi. Then we have another signal, let us call it Yi prime. Then what is the relation between Yi prime and this Xi? Yi prime, this discrete time signal, is Gi convolution Yi, which is nothing but Xi convolution Hi plus Zi. So, this convolution Gi. So, this convolution this or this convolution this, they are the same things. So, now when you convolve Gi with this, what do you get? Xi convolution Hi convolution Gi. Now, we can do this convolution first and then this, it does not matter, convolution is commutative operation, then Zi convolution Gi. Now, this is nothing but, what is the convolution of Hi and Gi? Gi is the inverse impulse response of the inverse filter of Hi. That means the convolution of Hi and Gi is just the delta function. So, when we convolve with Xi, it becomes Xi itself. So, we have simply Xi plus Zi convolution Gi. So, it is like as if the signal is just added with some noise. If we consider this as the whole, this whole thing as the channel, this whole thing as a channel, then what is happening in effect is that we are transmitting Xi, it is going through as it is, not through any filter, and it is added with some noise which is the convolution of Zi and Gi, and then we are receiving Yi prime. So, this is Xi plus Zi convolution Gi. Now, what is this? This is nothing but the additive Gaussian noise channel, except that this noise is now not white, but as we discussed before, the noise is a colored noise. It is no more a white noise. So, it is similar to, it is the same channel as we discussed as additive Gaussian noise with additive Gaussian noise channel with memory, where the noise is not white, but it is colored noise. So, by doing a simple operation of just putting an inverse filter at the receiver, we have converted the linear filter channel into a channel where which is additive Gaussian noise channel with colored noise, and the signal itself is otherwise unchanged. And just like this, we can also convert any additive Gaussian noise channel with colored noise into a linear filter channel also. So, what we have to do is put a so called whitening filter at the receiver, which will make the noise white, but then which will so what will happen is, if we take Xi, and suppose originally we have a colored noise, Zi colored Gaussian noise, then if we pass it through a whitening filter, how to design this filter we will not discuss now, but it can be designed. So, whitening filter, if you pass it through whitening filter, if this is Yi, this Yi prime will be Xi convolution this Gi, now Gi plus some Zi prime, which is Zi convolution Gi, and which is white Gaussian noise. So, we can convert a additive Gaussian noise channel with additive white colored Gaussian noise channel, additive colored Gaussian noise channel into a linear filter channel also by putting a whitening filter at the receiver. So, these two channels, linear filter channel and additive colored Gaussian noise channel or additive Gaussian noise channel with memory, they are actually equivalent. So, both of them equivalently, because they both are equivalent, any of them is called the additive Gaussian noise channel with memory. These two different ways, either linear filter or colored Gaussian noise, these two are just two different ways of thinking of additive Gaussian noise channel with memory. Okay. Now, we will discuss a very special channel model, which is which I think would be probably the most popular channel now to you, that is wireless channel. It is the channel model that we will discuss, which is very different from all the channels we have discussed so far in at least one aspect, and that is the channel changes with time. The behavior of the channel changes with time. So, first of all, let us discuss the different phenomena that the wirelessly transmitted signal goes through, then we will discuss the suitable model for wireless channel. So, such wireless channels are called fading channels, referred as fading channel or multipath fading channel or simply multipath channel for the reasons we will discuss now. So, what are the different ways the signal travels through space? Wireless channel is basically channels where there is no air, where the transmitter and the receiver are not connected by any wire. So, it may be through simply space, or it may be there may be some air or some other medium in between, or there may not be anything, it may be just vacuum. Okay. So, one mode of propagation is simply line of sight, simple line of sight propagation. This is the direct propagation. Then there are other phenomena that happens in the propagation. For example, reflection, where the signal is reflected from smooth surfaces around smooth large surfaces, and then diffraction. What is diffraction? The signal, when we transmit some signal from antenna, it is seen that even if there is some obstacle here, that we are transmitting some signal here, and if we put one antenna here, then we will still be receiving some signal, though there is an in between obstruction. So, from this phenomenon there are theories developed to justify reception of signal even in the shadow region, and one theory is that when wave propagates, every point in the wave front, so these are the wave fronts, then every point in the wave front behaves like point sources for the wave. So, from every point here, signal is transmitted in all directions. So, it is natural that we will also receive signal in the shadow of the obstruction. So, this phenomenon is called diffraction. This is the phenomenon by which signal travels even on the other side of the obstruction. And then scattering. It is seen that the actual received signal at the receiver antenna is often stronger than what can be predicted by reflection and diffraction models together. So, even if we take care of, even if we see all the reflecting surfaces and diffraction that could be happening, we cannot still account for all the signal strength that is received at the received antenna. So, another phenomenon that contributes to the propagation is scattering. So, this happens from all kinds of small objects or surfaces with roughness. So, rough surfaces or small objects. For example, there may be a lamp post or a tree or chair, table. These are all small objects from which signal is scattered in all directions. These are not reflectors, these are not large enough, or maybe sometimes these are not smooth enough to reflect the signal in one particular direction. But these signals, when they fall into these objects, they are scattered in all directions. So, that is called scattering. And the received signal at the receiver is most of the times the result of all these different modes of propagation. So, in summary, when we transmit a signal from an antenna and we receive the signal at the receiver antenna, the signal in between is propagating in different mechanisms: the direct propagation, reflection, diffraction and scattering, and the received signal is the resultant of all the signals that are received through all these mechanisms. And as one can now see, that signal propagates from the transmit antenna to the received antenna by travelling through multiple paths. It may be getting reflected from somewhere, it may propagate directly along one path, it may get scattered from somewhere and reach the receiver antenna along one path. So, it may get scattered from here and actually go in all directions, but one of the rays can reach the receive antenna. So, and there are usually infinitely many such paths through which the signal is propagating to the receive antenna. So, this is called multipath channel. That is why wireless channel is called multipath channel. When the signal is travelling through multiple paths to the receive antenna. Okay. And it is quite interesting to think what will be the signal power that we will receive if the receiver antenna and the transmitter antenna are separated by a distance d. It is known that if we have only direct propagation, say if you have one antenna here, this is the transmit antenna and this is the receive antenna, this is separated by distance d, then if there is only one path, the line of sight direct propagation path, then the path attenuation, the gain, path gain is proportional to G is proportional to 1 by d square. Actually, it is proportional to d by lambda square. So, it also depends on the frequency of the signal. So, if we take only distance, it depends on the distance in this way, and however, if there are other mechanisms through which the signal is propagating, then this need not be the way the signal power here depends on the distance. It may in general depend in the following: d power mu, where mu is some constant, usually greater than mu greater than 2, and it is also usually less than 4. So, depending on what kind of channel it is, what kind of environment it is, the attenuation may depend on the distance between the transmit and receive antennas in this fashion for different mu values. Okay. So, for example, if there is only one reflecting surface, which is called the ground reflection model, where the signal passes, there is one direct path and there is one reflected from the ground, then mu is 4. So, the channel gain is proportional to 1 by d power 4. So, the different, so it depends on the environment usually. Okay. Now, this is about the average gain of the channel. This need not be the instantaneous gain, meaning by at any point of time the attenuation the signal will go through need not be proportional to this at any point of time. It is usually changing with time, because there may be obstruction at one point of time, there may not be obstruction at another point of time, and the channel itself may change because these antennas are moving relative to each other and so on. So, even though these things tell you about the average behavior of the channel based on the distance, they do not tell us what is the instantaneous behavior of the channel, how the channel changes with time. And that is the fact that channel changes with time due to the change of environment is known as the fading. So, the channel gain varies with time, and because of, so there are two things. One is the variance, the variance of the channel with time, and another is that the channel is going through multiple paths. And because the channel is going through multiple paths, it is like the received signal. For example, if we consider a continuous time version, yt will be, say, some attenuation times xt, let us call it say, take the discrete time version for simplicity, say yn is a0 xn plus a1 x n minus 1. There may be another path through which the signal is reaching the receiver with attenuation a1 and delay 1, and then we may have so many other paths, a2 attenuation times delayed by 2 and so on. So, let us just take three paths with 3 different delays. One is no delay, another is delay 1, another is delay 2, with 3 different attenuation levels, a0, a1 and a2. If this is the, and then of course we will have noise, the received signal will also have some noise. So, let us say n or nu n. Then it is like this signal is going through a filter. So, this is basically a filter with impulse response coefficients a0, a1, a2. This is the filter impulse response xn is going through. Then noise. So, multiple paths in the channel gives rise to a linear filter channel here, and these filter coefficients themselves might be changing with time. There may be, this path may be there at some point of time, there may not be this channel at some other point of time, because some reflector might have been there before and it may not be there now. So, a1 may be 0 at some point of time. So in general, all the channel coefficients are changing with time. So, there is a multipath channel, and the filter itself is changing with time. Now, there are different parameters of the wireless channel which specify how fast the channel is changing with time, or how much multipath is there, and such other things. For example, the length of this impulse response. So, in this case the length is 3, 0 to 2. This length is called the delay spread. In the continuous time case, usually these samples, this delay 1 will mean some microsecond or millisecond. So, this is the delay spread. It will have some, for the continuous time case, it will have some continuous ht So, this is the delay spread is the range of values of t for which Ht is non-zero. And then there is Doppler spread, which is basically the Doppler comes because when the environment is changing, or especially it is easy to conceptualize as the receiver or transmitter moving. When we have one transmit antenna and one receive antenna, let us say signal is passing to this from through different paths. Let us say there are these 4 paths, and this antenna, receiver antenna, is moving in this direction. Then these path lengths are increasing. So, the signal received through these paths, the frequency of them will decrease. So, this, suppose we are transmitting a sinusoidal signal from here, the received signal received from these 2 paths will have a smaller frequency than the transmitted frequency, and because these path lengths are decreasing as the receiver moves in this direction, the signal received through these paths will have a smaller frequency than the transmitted frequency. So, even though in the frequency domain we transmit one sinusoid at some frequency f naught, at the receiver we will receive some signal at smaller frequency, some signal at higher frequency, some signal here, some signal here. So, there will be a signal received around f naught, but if we transmit a single frequency, we will not receive a single frequency, but the frequency will be spread out in the frequency domain, and how much it is spread is, this is called the Doppler spread. We know that this is the Doppler, this shift of frequency is called the Doppler shift, but in this case there will not be a Doppler shift, but there will be a Doppler spread of the signal, because some paths, the frequency along some paths is decreasing and the frequency along some other paths is increasing, and as a result the transmitted signal on a single frequency will be spread out in a band of frequency, and so this band is called the Doppler spread. And also Doppler spread, as you can see, how much the spread is will also tell you how fast the receiver or transmitter are moving with respect to each other. If they move faster, there will be a larger spread. If they move slower, then there will be a smaller spread. So, the Doppler spread has relation with what is known as coherence time. Coherence time, which denotes what is the time interval after which the channel response is independent of the previous time. So, that is how fast the channel is changing, and similarly there is coherence bandwidth, which depends on the Doppler on the delay spread, and we will not discuss this in more detail. If you are interested, you can look at any wireless communication book, either by Rappaport, Fundamentals of Mobile Wireless Communication, there is a book by David Say and Vishwanath. Both the books are available in Indian edition now, not very costly. Okay. So, this is also some fundamentals of wireless communication. So, please look at these 2 books if you are interested more into wireless communication and wireless channels in general, and we will just summarize by saying that wireless channel model, simply one can say that we have a linear filter which depends on time. So, H usually it is denoted by 2 time, this is xt, and this is, then there is noise. So, H tau is the impulse response at time t, and as time progresses the channel itself, impulse response itself is changing with time. So, there are 2 time, one is the axis in the impulse response, the other is the to denote the time index with which the impulse response is changing. So, in this class we have discussed linear filter channel. First of all, we have discussed continuous valued channel, unlike discrete valued channel that we have discussed in the last class. Then we have discussed continuous time or waveform channel, then linear filter discrete time as well as continuous time channel, and then we have discussed wireless fading channel in little more detail, seeing what happens in a real physical wireless channel and also the channel model for such channel. We will possibly use some of the channel models that we have discussed in these 2 classes, and even if we don't discuss some of these channels, it is quite important to know that such channels exist and they are important in general. Thank you.